I want to talk today about looking at functional programming principles and how you can take them and apply them to entire systems or even entire organizations. Now, Jet.com was an e-commerce company that was founded not quite 5 years ago. It's headquartered in Hoboken, New Jersey. Jet.com's original plan was to take on Amazon head on. About a year after launch, Walmart acquired Jet, and Jet now focuses more on the urban millennial customer, while Walmart.com focuses on the mass market. The two companies were built independently. However, ideally, we wouldn't have different supply chains for all the different branches of the business. Jet.com, Walmart.com, all of the Walmart stores, or any of the other acquisitions that we make. However, while unifying the supply chains has a lot of obvious benefits, it's not a small undertaking. Now, you'll notice my role is Director of Engineering. However, that usually denotes a manager position, but for me, it's more of an architect position. My role is to build and design the next generation unified supply chain for Jet.com, Walmart.com, and all of the other branches of the organization. After the acquisition of Jet, for the first few months, we had just started the early integrations, not the full-fledged integrations of the teams or the systems. Turns out in an organization this big, surprise, there are a lot of politics. One of the reasons that Walmart had bought Jet is because our tech was transformative. It looked cool. Not quite as cool as our offices, but it was up there. However, not everyone is going to settle for cool. Not everyone was convinced that our techniques would have real-world benefits. Well, it wasn't long before we were fortunate enough to have the opportunity to demonstrate these benefits. And when I say that we were fortunate, what I really mean is that disaster struck. Middle of March last year, in the middle of the night, I got paged for some kind of system alert. I woke up, hopped on the bridge in case anyone else wanted to talk, and was very shortly followed by team members from a bunch of other teams. It turned out that our production Kafka cluster was down. If you're not familiar with Kafka, it is basically a very scalable message queue system for pub/sub work. It is the primary method of communication among all of the tier 2 services at Jet, and it was at a dead stop. Before too long, we realized that the cluster wasn't just down temporarily, but it was completely dead. Every single message in flight in Kafka was gone. The customer orders, the replenishment requests, the catalog updates, inventory updates, warehouse replenishment requests, pricing updates, every single one was completely gone. We are going to have to rebuild the cluster from the ground up. Now, this could have been catastrophic. This could have been the end of the grand Jet experiment, enough to convince our new Walmart compatriots that Jet's technical tenets, while they sounded good on paper and they sounded cool, weren't really going to work in a real enterprise compared to tried and true systems and old ways of doing things. So what happened? Well, I'm going to make you wait till the end to find out. First, I want to talk about those Jet.com software tenets. Not just what Jet built, but why. Much of that is founded in the principles of functional programming. Lessons learned from those principles can then be scaled up and influence system design in the large. Then we'll talk about the real-world benefits of building and operating systems in this style. So what are the principles of functional programming? There are a lot of them, and I'm not going to talk about all of them today. I'm going to focus on just a handful. The ones I've selected are immutability, actions not objects, and to embrace purity. When I talk about immutability, I mean in functional programming, you don't change the state directly. Your input messages don't change, and the function will then produce an output from those input messages that itself will not have changed at all and never will change. The state is not directly mutated. The second point is the idea of actions over objects. In an object-oriented world, you're thinking about the things. In a functional world, you're thinking about what you're doing. What is the workflow that's involved? And the third point about embracing purity. We avoid writing functions that produce side effects. We don't write to disk or write to network until the last possible moment, and we strictly control those side effects when we do. The external world doesn't, outside the function, doesn't affect anything inside the function, and nothing inside the function can change anything about the outside world. This makes it very easy to reason about the code and to test the code. It's very predictable, and it produces the same results every time for, if you have this single input and single output. A benefit of it is functions become referentially transparent. That term means that if you know the inputs in advance, or you've seen that input before, you can replace the entire, possibly expensive computation with a pre-computed cache of the result. So now we're thinking functionally. What does it mean to design functionally? Going back to those 3 points I listed earlier, start with immutability. Now, one of the first parts of immutability is something that most people are doing nowadays. It's pretty ubiquitous, and that's the idea of message-based communication. Systems will communicate to each other synchronously over HTTP message passing or asynchronously over some kind of queuing mechanism. The second concept that you get from immutability isn't nearly as ubiquitous, and that's event sourcing. Events don't change. Once an event occurs, it always will have occurred. You're not going to go undo that event. In an event sourcing system, events are first-class citizens, and streams of events are what you store for your canonical data store. You still have state, you still have a concept of state like in a traditional system, but state is secondary. In an event sourcing system, the state is usually in the form of a snapshot of the event stream. It is an aggregate function that has been applied to the stream of events, like a sum or a fold over all of those events. State is an interpretation of those events, and that interpretation can change. You may decide you want a new aggregate function to provide a new interpretation of those events. Maybe if you have a stream of numbers, you want a median instead of a mean. If you want to produce a new aggregate function, a new view of that state, you can create the new function and apply it over the entire stream of events that you have, and that will never change. The second point is about actions, not objects. Another way of looking at this is that we deal in verbs, not nouns. We don't build entity services. There isn't a monolithic customer account service like you might find or expect if you're coming from an object-oriented mindset. We identify workflows, the things you're trying to accomplish, and we build and we name services according to those verbs. And the third part about embracing purity. In the same way that it allows better testability and easier understanding and reasoning of individual functions, purity allows you to plug together systems more easily. Referential transparency, as I mentioned earlier, becomes important here. It permits large-scale refactoring, not just of systems, but of systems of systems. Maybe you have a transportation system that calculates time in transit from zip code A, where the warehouse location, to zip code B, where the customer is located. This is going to be a pretty expensive computation under most circumstances. Advances in tech make it feasible to pre-compute all of the combinations, turning this expensive computation into a cheap point lookup in a key value store. The inputs and outputs of the system as a whole have not changed because of referential transparency. You've just turned the computation into data. And now that lookup is so cheap that maybe you can use that on every single product page instead of just at checkout, which gives the customer a better experience. Now let's dig into a real-world system that was designed following these principles. Now, an aside about naming. Most systems at Jet.com have been named after superheroes, but after a couple years of building a lot of systems, a lot of the obvious names have been taken. So about 2 years ago, when building a new system, I tried to come up with a name of a superhero name that most people didn't know about right now or at the time, but by today, a lot of people would know and might have some kind of clout or cachet. So allow me to introduce Panther. Now, I couldn't get the rights from Marvel for any of the officially licensed media, but I like this picture better anyway. Panther is the inventory tracking and reservation management system for Jet.com. On the supply side, it aggregates and tracks all sources of inventory. These can be Jet or Walmart-owned warehouses, or they could be third-party merchant warehouses. On the demand side, it acts as the source of truth for reservations against the available inventory. When a customer is checking out, the contents of their cart are reserved. If the inventory is not available at the point of checkout, the item either has to be resourced from another location or a new item has to be selected. Between the two, the primary goals of the system are to maximize on-site availability while minimizing reject rates due to inventory unavailability. Our secondary goals were to improve the customer experience by reserving inventory earlier in the pipeline. We wanted to enhance insights for the marketing and analytics team by providing more historical data and better analytics. We wanted to unify the inventory management responsibilities that had traditionally been spread across multiple systems. Now, of course, with all of these business goals, we also had a lot of non-functional goals like high availability, geo-replication, and fast performance due to SLA, or with really strict SLAs. So how do we build a system like that? What we're looking at here is the basic building block of systems at Jet. We start with a stream of commands that are executed against aggregates that produce events that are then stored in event streams. We use this for every domain at Jet. Now, let's walk through all of these in a little bit more detail. In the very first step, we have this stream of commands we want to execute. This can be broken down further into 5 sub-steps. First, we want to ingest the message be coming in over Kafka, HTTP, some kind of queue, and the message itself could be in JSON, protobuf, Avro, whatever works for you. The key is that in your language of choice, you then deserialize that message to a strongly typed command. Command is a message that expresses intent to change state. It's named with an imperative verb and usually a direct object. Some examples here are update inventory, reserve inventory, expire reservation. Now, commands are usually pretty shallow, flat objects. You start with the name at the top, then one or more identifiers to point out which aggregate you want to change, then whatever values may be important for that. In this case, we want to talk about what the quantity that we're dealing with. And then there's going to be a little bit of metadata for, in this case, who triggered the event and at what time. Using the identifiers from the command, you then retrieve the current state from the data store. There are a few different ways of constructing this state, which we'll get into a little bit later, but now just assume that state, or if you prefer domain-driven design language, the aggregate is stored somewhere. For inventory commands, the appropriate identifiers are going to be the warehouse ID and the item ID. This will retrieve the current inventory counts for that item at that warehouse. The other thing that we retrieve at the same time, and this will become important a little bit, is that we retrieve a logical clock for that state. It is a monotonically increasing integer that identifies the last update or last event in that stream. If that clock is called the sequence number. If there have been 1 million updates to that stream, then the sequence number will be at 1 million. So now that we have a command describing intent and the current state that we want to change, we then execute the command against the state. It executes the business logic, usually consisting of some kind of validation rules. In some cases, the command is coming straight from the source of truth. For example, the update inventory command is going to be coming straight from the warehouse or straight from the merchant. They're the source of truth for what their inventory counts are, so the validation of that command is trivial. In others, like in reserve inventory, there is validation that needs to happen. If the quantity being reserved is greater than or equal to, or greater than the amount that we have in stock, then we have to fail the reservation. However, if the quantity is lower than we have available in stock, then great, it works. An important point is that executing the command does not itself change the state. It is a pure function. It does not induce any side effect. So what does it do? It produces an event. An event represents the change state. It indicates that something has happened. It usually flips the syntax of the command that triggered it, switching to a past tense of the verb. The update inventory command turns into an inventory updated event. The reserve inventory command is swapped to inventory reserved. Failures are events too. If a reservation fails, instead of having a successful inventory reserved command, we'll call it reserve inventory failed. So now we have an output event in hand that we want to commit to the event stream. Everything up to this point has been done entirely in memory using pure functions. Nothing has been saved. This event is only provisional until it's committed. We will attempt to write the event to the stream at the next sequence number. If the write's successful, then the event at that point has officially happened. If the write attempt fails due to a conflicting write, another writer has already written an event at that sequence number, then this event is invalidated. We have to re-retrieve the new state and re-execute the original command against the new state. Now, it should be noted that this method of executing commands, or really just processing a stream, lends itself extremely well to a functional style of coding. We are starting with our immutable set of input commands. We're running them through a chain of stateless functions and producing a set of events immutable as output. So now we have an event stream. You can't just look at the latest event and know what the state is. Reserve inventory or an inventory reserved event will tell you a little bit, but it's not going to tell you how much is available in total. So how do we build the current state? And again, while you can do this in pretty much any language, this is extremely well suited for a functional style. You need to define three things. First, an initial or a zero state. This is pretty easy in our example. We have an unknown item at an unknown warehouse with a quantity of 0. Then you need an apply function that takes a state and a single arbitrary event as parameters and applies the event to that state. And this is where the meat of the business logic usually is. And that's the case here. We know every single event that the system can possibly produce, so we will write business logic for each. In the inventory updated event, the on-hand will be reset to whatever the merchant tells us, and any of the outstanding reservations that have completed but we've kept around for accounting purposes, we can just get rid of those. After inventory reserved, for example, the on-hand would stay the same, but the total reserved would increment by 5, and the available to sell would similarly be decremented by 5. And third, we need a fold function. It takes the apply function we just described, an arbitrary state, and a sequence of events to apply to that state. And this is exactly what the Snapshot Event Stream service does. We read in a batch of just committed events, retrieve the latest snapshot from the data store, apply the entire batch of events, and overwrite the old snapshot with the new one. So now we understand that core flow, that core pattern. Let's look at it inside an entire system. And we can see in the yellow box that the core flow is untouched. We have input mappers on the outside or on the front side that bring in the data from the external systems, and we have outbound mappers for any downstream consumers, mapping to whatever contracts we have in place. We see that on the front side, the inputs can be asynchronous, like on the bottom flow coming in through Kafka, or they can be synchronous if they're coming in through HTTP if you need some kind of faster response. The downstream consumers may not need to know every single snapshot or every single event. Maybe one particular mart or storefront will only care about some subset of the items available. You can do any of your mapping to outbound contracts or filtering down to a particular subset at that stage, completely statelessly. A very important part of all of this is where you store the events, where you store your snapshots. So let's talk about storage. Event stream storage has several criteria that you don't necessarily see in other systems. And we're going to talk about it in 3 different ways. First, we need an event stream storage. One of the criteria is that it needs optimistic concurrency on event writes. In many, if not most circumstances, the command executors are running in parallel and trying to trying to write to event 1000 on the same stream concurrently. One of them should fail. The validity of the second event may be affected by the first. Instead of blindly writing to the next point in the event stream, the second executor should instead notice that there has been a change and be able to throw out that provisional event and retry the whole thing. This ensures that the streams are strictly serialized. However, because stream processing is strictly serialized, the write latencies become extremely important. Your maximum throughput for the stream is going to be defined by how quickly you can write each event individually. If you can only process or only write an event in 100 milliseconds, then you're only going to get 10 events per second in your stream. So this is a pretty tricky requirement when you also are trying to do geo-replication. There's a big trade-off here between consistency and the latency here. The next point is you need something or somewhere to store your snapshots. You want a low latency, high throughput reads and writes of individual documents that represent a snapshot or aggregate of a stream. You may want these to be queryable as well, but for the most part, these will be point lookups. The third point is the one that's one of the hardest to get, and that is a good change data capture system. Every single event, once committed, needs to be published for any downstream consumer. This ensures that if and only if the event has been written, that it will go downstream, eliminating dual writes, which is one of the biggest pain points for resiliency in any kind of distributed system. This allows a lot of other things like snapshot service being run asynchronously instead of synchronously, and allowing any downstream consumer to know immediately that there has been some kind of change in state in your system. Change data capture doesn't just apply to events. Maybe your downstream consumer doesn't care about every single event that you've done, every reservation. Maybe they only care about, do you have a PlayStation 4 in stock or not? So having a change data capture for your snapshot store is just as important as your event store. We have chosen Azure Cosmos DB because it fits a lot of these requirements brilliantly. I could easily do a whole talk about comparing and contrasting different data stores for these kinds of requirements. I don't have that time here, so we'll talk about that later. But if you want to find me afterward to talk about how, say, Cassandra would compare, I'd love to do that. So now that we've looked at what the system design looks like, what are the benefits? What do you get from designing a system in this way compared to a normal way? The first big point is resiliency. For me, a system is resilient when it stays functional with little or no customer impact in case of a partial outage. Recovery from outages is trivial, and the errors are trivially corrected or self-correcting. So what are some types of errors or problems that fall into this category? The first one is bugs in our code. It happens to all of us. We all have bugs. With an event stream, we can, and the commands that we deal with this, we can look back in time, find where the bug was, write new code, deploy it without having to worry about any kind of schema changes and the like, and just rerun from wherever the bug happened. The next is dealing with out-of-order messages. Now, this can get pretty complicated, and it's hard to deal with in a lot of systems. Event sourcing makes this a lot easier. There are a lot of times when in systems like the inventory tracking, we are getting out-of-order messages from all the different sources, from warehouses, order management systems, third-party merchants who are giving us updates. So we deal with this by using learnings from conflict-free replicated data types and other lattice-based structures, which sounds complicated, but what it really means is that we make sure that our event handling is always idempotent and commutative. We do this by making sure our state generation is purely additive. And that can be literally additive, that we're only adding new items onto the state snapshot, or that it is logically additive, that the state changes are all monotonic. The sequence numbers are always increasing, or in the case of a reservation, once an order has been shipped, it's never going to go back into a created state or a just reserved state. It's only moving forward in the logical process. There can be problems with downstream consumers who lose data. Maybe they have their own bugs, or maybe their own data store died. We can replay the events and get them back to where they were. If it's been recent, they can themselves just read from the Kafka stream that's between us. But if it needs to go much further back, we can always replay from our own data store and push it out through the change data capture for them to read again. We can deal with random restarts trivially. Functions are stateless. All of the microservices that we saw there are stateless. You can do chaos testing against them, take them all down, bring them back up, and everything will continue to work perfectly. We can deal with entire regional outages. We can run hot pretty trivially where it's necessary in our tier 1 or customer-facing systems. With the data store we've selected, we can change the right region within seconds, or we could run multi-master. And for the parts that we don't need to be running everything hot, because everything is a function, it's stateless, and the way that we deploy it, which I'll talk about in a moment, we can scale up an entire secondary region within seconds. One of the other benefits is that it's super easy to add features. Merchant snapshot expiration was a feature that we wanted to add. Old inventory is not helpful for us. If a merchant told us a month ago they have something, we can't rely on that anymore. So we wanted a way to get rid of the old data. Now, a single engineer with light F# training who just joined, had no cloud microservice background, was able to implement this feature from design to production in under 3 weeks, with the result of dropping our 3P reject rate in half, from 0.8% to 0.4%. In fact, the entire system was built with not very many people. In 2016, we had 1 engineer. Only 3 had delivered the system by holiday of 2016. And by a year later, there were only 5 people working on this entire thing. One of the really cool features is that event sourcing gives you a time machine. You can see the state at any point in time, whether a day ago, a month ago, a year ago. You can walk step by step through everything that has ever happened in the system. This is amazing for troubleshooting. You can validate behaviors that people are seeing. If it said there was a problem a month ago, you can go back in time, re-observe the problem, and do a full root cause analysis on it. Having events like this is great for auditing, and it's great for analytics purposes. Scaling is super easy when you're using these functional techniques. Scaling in practice happens along 2 dimensions, compute and storage. With compute, our microservices, being completely stateless, are very easy to deploy and schedule in Kubernetes or Nomad. They're all independently deployable, all independently scalable. On the data store side, again, the data store that we've selected is scalable throughput within seconds. Go from the baseline to 10 or 20x of the throughput. And as far as the amount of storage is concerned, as any given partition gets too big, it will automatically split if it gets too full. And as an example, there was a time where an external merchant started sending us way too many updates, thousands of times more than they actually needed to send us. Our total throughput overnight went to 250% of what it normally was. It was trivial for us to just scale everything up within seconds, until we were able to work with the merchant to get them to fix their problem. And as soon as we got off the phone with them, we were able to scale everything back down to normal, which would allow to huge cost savings without breaking any of our SLAs. Testability is huge with this. 100% of our domain logic is unit testable. Our command execution has no external dependencies and has no side effects. The application of events to build new state, again, completely pure, no side effects. With these pure functions, we can identify every single possible path provably through the business code. Not only that, we don't just write unit tests. We can write complete executable specifications, properties of invariance that we can assign to our code that can be checked with large numbers of randomized input. There are a lot of different tools for doing this. They work a lot better when you're working with functional systems. So what happened? We've gone through all of the benefits of the systems designed like this. What is the end result? What happened with that Kafka cluster? It turned out to be a non-event. What could have been catastrophic was little more than a minor blip and a little bit of annoyance for people working in the middle of the night. we were able to rebuild the Kafka cluster from scratch by using standard techniques of just paving it over and putting out new nodes. And then while we were doing that, we contacted all of the teams who owned systems at the edge of the Jet system. Anyone who had systems talking to, or taking customer inputs, or had APIs exposed to merchants. All of these systems, we got the people online, and as soon as the Kafka cluster was ready, we had those team members just set their checkpoints back in their event stream to right before when the problem happened. All of those events from the edge of the network were then replayed to all of the internal systems, who then were in turn able to reprocess those, or if they had seen them before, or process them for the first time. Now that's a huge flood of events, but all of these systems were able to scale up massively to deal with that load and keep everything within SLA. Despite this problem, this huge problem of losing all of this data, not a single customer order was delayed at all. So we're very happy with that result. So recommended reading, if you are interested in more of this data design, I recommend a book by Martin Kleppman, Designing Data-Intensive Applications. And if you're interested in how to build domains in a functional language like F#, I highly recommend Domain Modeling Made Functional by Scott Woloshin. And I'll be around the rest of the day if you want to talk anymore. Thank you very much.